All right. The evolution of Android graphics, focusing on Android 10 through 13, and for the rest of the presentation, I'm going to try not to read off the slides. So thank you for coming to this very final session here at DroidCon SF 2022. I'm Dan Galpin. I have been around Android for a very long time, wearing a whole bunch of different hats, and it has been a lot of fun. It's been 12 years now, and I've been to many places, and it is great to be back here in San Francisco. I live just south of here in Mountain View. We're going to start talking about some of this with some ancient Android history that I was kind of watching. And by watching, I mean like I was there in the office when like Romain was sweating how to build hardware UI originally when we were working on Honeycomb. Not that I was actually building it myself, because he proved to me that I shouldn't be building this when he told me about these 7 million permutations of shaders that it would automatically generate and stuff like that. And we're going to get to actual like stuff that you can do with this eventually, but we're going to start with history because history is fun. So let's take a trip back. That's what our website used to look like back in the days of Android 1.1. Isn't it cute? And in the beginning, we had OpenGLES 1, kind of. If you actually remember from the old days, you'd run the emulator, and the emulator would run faster running in ARM mode than it would run in Intel mode. I don't know how many people remember that, but it's true. And the reason why was that we had written this really cool OpenGL emulator that was totally optimized for ARM, and it actually turned everything into ARM assembly instructions, and that made things really fast, even on the emulator, which was running an emulated ARM chip. Amazing. We were using 565 buffers. I can't really see it on this TV, but like actually it makes banding happen everywhere. If you remember like old Android, you saw banding all over the place. We actually didn't have hardware floating point built into the system. So like when it comes to graphics, that means that you're constantly trying to shift to using fixed point anywhere because it's going to be so much faster. And we also did immediate mode rendering. Now a lot of people said Android didn't used to have hardware acceleration for graphics in Android 1.0, and that's only mostly true. We actually did have hardware acceleration for things like compositing and important things like that, but the actual drawing of the bits when you did your views was all done in software. And we still, even back then, in Android 1.0, we had this concept of a shader, which is kind of amazing, and they were largely used to make gradients, ones that were very heavily banded, if you remember. And you could even use them to tile a canvas with a bitmap texture, so you could actually put bitmaps on things, and you could compose them together for advanced effects. And so this was all in Android 1.0. It's mind-blowing. And basically, this is what it looked like. You had two choices back in that ancient times. You could use a canvas, and that talked to the SCIA graphics layer, and that rendered everything into a buffer, and it went to surface. Or you could just talk to OpenGLES, and you could put stuff on a surface that way. RenderScript was introduced fairly early, actually, and it was put there in Eclair on Nexus 1 to draw things like this. And it was basically, the idea was we wanted to have a way to write high-performance graphics and compute across heterogeneous hardware, and without having to resort to separate paths for C and C++ and GPU kernels, and it was actually made a public API in Honeycomb, and then in Jelly Bean, we actually expanded this to include all these really cool intrinsics, some of which maybe you still use. Does anyone here use RenderScript intrinsics, by the way? Okay, a couple of you. Yeah, they're pretty cool. We actually deprecated the OpenGL interface before we introduced intrinsics, so so let's talk about accelerated rendering, which means you have to go back to Android 3.0, which was all about bringing Android to tablets. And this is really a big problem. I mean, this is like, I stole this slide. I'm like, I'm not going to make this again. Because we suddenly had this huge growth in pixels. Like back then, tablets actually had more pixels than phones, hard to believe. And we had negative growth in the memcopy speed. And so suddenly we were like, we have to make this thing look good, and we have no memory bandwidth to do it, which means we can't just render everything into a large buffer. So we created this thing called hardware UI, which was completely separate from SCIA. And that hardware UI actually would go straight to OpenGLES 2 or higher. And alternatively, you could still render to the SCIA graphics layer. And it works approximately like this. We also introduced this animation system. I'll talk a little bit more about then. But basically, you set an event, it invalidates, it creates display lists, and these display lists are hopefully not changing very much. And so it actually changed the way view invalidation worked entirely. Up until this point, if you invalidated a view, it meant that all the views below it redrew. And now all of a sudden, we actually were taking account of what you actually invalidated, and everything beneath it does not truly redraw, it just comes out of the display list. And that's really important when it comes to dealing with GPU acceleration, because so much of GPU acceleration is based on the cost of state changes. And every time you make a call into these things, it's expensive. And every time you have to make a call from the view logic to actually create these display lists, it's even more expensive. So again, the way it works is you can approximately think of it this way. Every view turns into a little display list. And you know, we referred to these internally as render nodes, which is kind of important. And Honeycomb was even more challenging because we did crazy things in the UI, like having gradient backgrounds on lists, which means we had to have, in addition to all the other stuff of having like a giant number of pixels and having a very small amount of memory bandwidth, we also made things worse by requiring everything be alpha blended. So we had like layers and alpha, and so we actually created something to do both things at once. So first of all, we knew we had to have a way for you to opt out easily from doing hardware rendering, so we created hardware layers and software layers. And that allows you to do stuff like, I want to pre-render this background thing into one layer, and then I want to save that off so I never ever render that or touch that again. That just sits there, and then I'm going to instead, and I'm going to have some software layers because not everything worked. And so this is what we didn't cover in Android 3.0, which seems like a lot, and there were a lot of places where this didn't cover things we needed. But as it turns out, this was enough to get most of the apps running entirely in hardware acceleration on Android 3. We slowly worked on this to add more and more stuff to it in Android 4. And 4.3, we introduced OpenGL ES3, which was really nice. And then by the time we got to 4.3, like, it's actually starting to feel like we were getting there. We introduced Vulkan in NuGet, and then in Android 9, almost everything started to work. And this is almost not fair because draw vertices should have worked in Android 9, but no one actually commented out the line that said don't use this. We did that in Android 10. And actually set linear text and set mask filter also both kind of worked. Set mask filter doesn't work with emboss masks and still doesn't today, so don't use those unless you want to go to a software layer. Okay, and why did this all happen? Because in Android 9, we decided, you know what? We've been working on Skia for all these other projects. We are doing Skia for Chrome. We are doing Skia for, Chrome, Android. Pretty much every time we do 2D at Google, we are using Skia. So we've been working on it, and so we actually added a ton of features into it, things like path ops and color space support, and most importantly, we added an entire OpenGL and a Vulkan backend. And so we saw in Android, instead of wanting to rewrite the entire backend when Vulkan came around, we decided to switch back to Skia. Now, we couldn't completely switch back to Skia. Because we've done a lot of stuff to optimize things around the way the UI worked, particularly all those render nodes I mentioned. And those render nodes are what allows animation to work smoothly and easily on Android. So basically, in addition to each one of those render nodes containing a display list, they also contain those view properties that you use to animate things like position offsets, like rotation, like scale, all these things that you can do, and they're almost free because those are all just being applied to that particular render node. So all that stuff stayed, and it also did things like deorder and shadows, and so we layered that on top of Skia, and Skia is just used now for these display lists, these kind of recording canvases, as we call them, and HWI still manages all that above. So. And the way this works now is we also added this render thread, and so I'm not even like, remember the last diagram that I showed, like, okay, this is all the stuff that's in the system, and that's all the stuff that's in kind of surface. This is actually even only half the story because the rest of it didn't fit on the slide. But this is basically what's going on, and it's not even fully correct because there's not actually a direct line. At some point in the middle of all of this, the UI thread is starting to send buffers to the render thread, and the render thread is doing these things like preparing the tree, flushing commands, and actually sending them out to the GPU in parallel. And this is important because at this point, Android also has lots of CPUs, and so it's really important to actually make use of them to make UI fast. So what I'm saying is that this is really complicated, and it's actually pretty cool that it works. The good news is that now we're actually, on one CPU, we're actually doing all these things to layout and record display lists and all this kind of stuff. On the other CPU, we're actually sending stuff out to the GPU and also doing a few built-in animations, like that's how ripple effect works and a few things like that. But for the most part, this is what RenderThread is doing. And then Android 10 upgraded to Vulkan 1.1. And this is really important only because this finally added all the features we needed to really have the compositor and UI system use Vulkan. There were a few things that 1.0 lacked. And this also introduced the Angle project. And that allows an OpenGL driver, essentially, and not Angle is a generic graphics engine that sits on top of other graphics APIs and basically gives you an OpenGL interface. And so what this means is that this enables this kind of future, which is not here today, I mean it's clear, where at some point Vulkan will become the only graphics layer you use to talk, or maybe even the only layer that's used to talk to the GPU, and you can talk to it directly, you can talk to it through Angle, you can talk to it through hardware UI and Canvas and Skia, and this means that our OEMs and ISVs and everyone who's building drivers can actually focus on making great Vulkan drivers, and this is closer to how things are working today. There's at least one device that I believe is shipping like this. But that also means that we want them to focus, and that meant that we had to figure out what to do with RenderScript, and the conclusion was to get rid of it. And there's a lot of reasons. I think that when you look at this, you say, one is that RenderScript was only Android. And everyone's like, well, we don't want to write custom code for Android for things that are as complicated as compute, if possible. Vulkan was there, and Vulkan actually, it turns out, is a pretty good compute API. It supports the things that RenderScript does. It doesn't support CPU compute, but it supports everything else. And the thing is, it's not going away yet. It's still there in Android 13. But what it does mean is that you're unlikely to get GPU-accelerated drivers. For the most part, those are gone. There's a couple devices that still support them, but if you want to get on the GPU, RenderScript is not going to help you. So evolving graphics. So Android 10, with finally Skia, everything that is all in place, we were finally able to actually move graphics forward. And so what we did, again, Vulkan 1.1, we added a bunch of new things. We added hardware renderer, we added access to render node, we added access to something called recording canvas. And render node is really important because render node actually separates the display list and the hardware rendering from the view system. And as you can imagine, this is really cool for Jetpack Compose. And in fact, Jetpack Compose does use this as much as it possibly can. And if you look at the back end for Jetpack Compose, it does some really sneaky things to use render node even before Android 10. But it also has falls back to the view system. We also added some cool things like surface control, which is actually both in the NDK and the platform, as well as surface transaction stats. You can actually see like what kind of rendering quality you're getting. So all this stuff was like really big. Android 10 was a great release for this. We added a bunch of interesting stuff in Android 11. The Android image decoder made it in there, and we added things like get hardware buffer, which is really cool. So now you can actually use NDK stuff to render into hardware buffer and make a bitmap without having to do a bunch of extra copies. So Android 11 definitely helps if you're trying to use C++ and Vulkan code to manipulate graphics. And in 12 and 13, as I said, we added RenderEffect. This allows you to do things like blur and color filter and apply them to a render node yourself, which is sweet. You can also use view.setRenderEffect to actually apply them directly to a view, so it's pretty trivial. And you can use them in Compose. I'll show that in a second. And then we also added RuntimeShader in Android 13. And this is finally kind of brings along the promise that we suggested would happen in Android 1.0 when we showed that shader in the beginning. We now actually have programmable effects available in the pipeline, and I'll show you kind of what that means too. So let's talk about Vulkan Compute. I'm not going to spend a lot of time on this, but I'm curious, is there anyone who would like to see a full talk on Vulkan Compute and how to do it? Okay, I see like 6 or 7 hands. All right, this is not that talk, but I will talk a little bit about Vulkan Compute and why I think it's interesting, and maybe more interesting than Vulkan itself. Okay, so this is an extremely simplified version of the Vulkan pipeline. And why I see simplified, I mean the fragment shader has like 4 stages. But this is kind of this. What's great about Vulkan is it actually provides a really good model for what's really going on in the hardware of your GPU. But it is known to be incredibly difficult and ponderous to compose, to actually code for. And in some ways, it's great because it actually you get to handle things like memory barriers. You get to know about workloads and jobs. A lot of things that as a graphics programmer you really don't want to deal with, but you can. However, if you look at the compute pipeline for Vulkan, it is incredibly simple. You have an input assembler, you have a compute shader, and you have an output. There's 2 stages to the pipeline. Itself, pretty straightforward. And that's not really a simplification. That is basically the pipeline. Now, that doesn't mean this is easy. But what I'm saying is, for compute, actually Vulkan does not make you do a lot more than what you'd expect to do in a compute environment and gives you the right controls. Like, you actually do want to know about things like being able to make sure that you are using the correct primitives to make sure your jobs don't smash each other, et cetera. So here's kind of what this actually looks like. Now, this is what you basically have to do in compute, okay? And I'm not going to go through all of this, but basically you have to do a bunch of stuff to get a device because Vulkan basically separates out the concept of device from initialization. So you initialize Vulkan, and then you say, okay, I need a device. I need a device that has these specific parameters, like supports compute, and then you go and you actually create pools, allocate command buffers, lay out your pipelines, which you'd want to do in any kind of compute sense anyways, because you need to know the kind of workloads you're expecting, create your buffers, record your commands, submit them, and then wait for it to be idle and everything to be done. So that's kind of what it looks like at a very, very high level. And this is the kind of compute shader you might run. Probably not this one. All this one does is do a color filter, but this kind of shows you kind of the very, very simplest possible thing you could do. And the reason I'm showing this particular one is because we actually implement this in RenderScript, and I'm also going to implement this later on. So what we do have, however, if you're interested in playing with compute, is we have this really cool RenderScript migration sample, which seems like, oh, well, if I'm not doing RenderScript, it's probably not interesting, but it actually shows you how to build an entire Vulkan compute pipeline in about the simplest possible form. So it's actually really cool. We also have, Google has worked on this, not Android, a prototype OpenCL-C to Vulkan compute shader compiler. Both OpenCL and Vulkan use SpearV as their intermediate form, but they're completely different. However, with a little bit of mashing together, some will actually work. So for people who are using OpenCL on a desktop app or on an app on another platform, you can actually use this to, in some cases, just bring that compute right along and run it within Vulkan. So that's kind of cool. And also the RenderScript migration guide is pretty great. Okay, so this is kind of like not the end of the talk, by the way. But this is basically, if you really want to do compute and you want to run it on the GPU in previous to Android 10, use RenderScript still. Use Vulkan for Android 10 Plus. If you really care about performance, that's the way to go, and compatibility. Now, RenderScript Intrinsics, we've actually done something. So first of all, we actually have this thing called the RenderScript Intrinsics Replacement Toolkit. It's an open source NDK project. And basically what we've done is we've taken all the CPU optimized stuff from RenderScript, which is actually really fast, and we've just put it into a library. It handles threading, and it creates these little kernels, and it's really fast. It's actually way faster than running these things in RenderScript, you'll find. So if you actually care about performance, and honestly, most of those things never ran on the GPU on most devices, so you're actually in pretty good luck using this toolkit. So if you just want to use a lot of that old RenderScript stuff, this is the way to do it, but you do have to include NDK in your project. Now, we do have, however, for some of the most used things, we have RenderEffect, which was an Android 12 thing. Make sure I get my versions of Android right here. And this is cool. So you can apply this to a view, or you can combine it to a graphics layer in Compose. In a view, you just call setRenderEffect, and you're done. You've now applied that render effect to your view. Pretty easy. In Compose, you actually can take the graphics layer, and you can literally apply that right inside of the modifier in the graphics layer. So again, very, very easy to do a blur on either one of these things, and they both work the same way. They're both using render node underneath the hood, as I mentioned. And this is, by the way, how you would actually use the RenderScript intrinsic. This is, it's actually a lot of code to use the existing intrinsic. One of the nice things about the RenderScript replacement library is it's actually much easier than this. You don't have to set up the kernel and allocate. It's much easier. But the important thing to note about this is that it eventually generates a bitmap. And that's a problem, because if you want to write code that's backwards compatible, that's going to run on old things, that generates a bitmap, you don't want to have new code that then alters your views. That's kind of a mess. And so fortunately, there's a solution, is that at the same time we introduced render node, we also introduced this thing called hardware renderer. And this is actually really cool. And I've never seen this documented. It probably is documented somewhere. But you can actually, when you actually create an image reader, you can create it with hardware buffer, and this uses that weird Kotlin syntax for, or. But all we're saying, if you use the correct parameters for hardware buffer, you end up with an image reader that creates a surface that can be rendered to. And so there we go. You can now create a hardware renderer. You can set the surface from that image reader. And then you can use this thing that I mentioned earlier called recording canvas to begin recording whatever you want to do. And then you can draw your bitmap. And you can apply render effects here just the same way. So using this technique, you can actually get all of this stuff into a bitmap. In fact, anytime you want to render something into a bitmap and you want to use the hardware composer and all of this cool stuff, not hardware composer, the hardware UI and all of this cool stuff, you can do it this way. So this is actually just kind of a nifty trick. If you want to ever do some caching yourself, probably don't need to do this. One of the really neat things about this also is that it uses okay, hold on, let me explain to you what this is doing. First of all, we create the render request here, and then we basically have to, we get the bitmap by wrapping this hardware buffer. And what's great about this is that we're not doing a bunch of copies. Like, this is all happening within Skia, and we're just passing these references around. And that's really the key thing here. Yes, there are a bunch of things that can happen that can go wrong. They don't, usually, so that's good. And that's it. So using this technique, you can actually go and create a bitmap that you render into without having to waste a lot of time or use the software renderer, which you had to do before Android 10. So we can apply a color filter effect this way using the built-in color matrix. This is a rotating hue effect. And the reason I chose this is because I'm not that great at writing shaders, to be honest, but I did want it to write something that I could actually demonstrate a shader in. And so let's talk about what we did in Android 13, which allows you to run your fragment shader in Android's graphics pipeline. So let's talk about fragment shaders and shading languages. And what they do is that when you think about that giant pipeline I put up earlier of all the stages that are going on in the GPU, you actually end up with a bunch of triangles, and at the very, very end, you say, what color is that triangle going to be, or that pixel in that triangle going to be in specific, and that is what a fragment shader does, which means they can do almost anything, because they're actually determining what that final output stage is going to look like. And they're written in this graphics programming language, and what's cool about them is it has this very, very low-level support for graphics and matrix types. Like things like vector, matrix, color, and normal, they just work, and in some ways it makes the language kind of mysterious until you've actually played with it, but actually once you've looked at it for a few hours, you realize that it's actually just very fast and very terse, and if you're a fan of Kotlin and its ability to do things in terse ways, you will love shading languages. And what's cool about them is that they are designed to execute on graphics hardware. So we have this little thing, this program that you can actually write, which you don't have to use the NDK or any other kind of tool chain for, that is ultimately going to end up getting executed directly on graphics hardware. And that means a lot. So let's talk a little bit about how AGS, oh wow, that's really squished. Let me know if anyone can read this if anyone's phone can read this QR code. I'm really curious. Because if you can't, then you're not going to be able to see any of the rest of them. That would be kind of sad. But if you can, that's awesome. And basically, there's a couple differences between AGSL and, okay, at least one person got it, good, and GLSL. This is, by the way, a shader that I wrote just to demonstrate the coordinate space. So if you put the same approximate shader into AGSL and GLSL, you end up getting different output. And yes, this is about the limit of my ability to write shaders. I can do a grid. There's a couple differences. It doesn't have preprocessor support. It uses a screen coordinate space, as you can see here. And you're also not writing the entire GPU fragment shader. You're writing just a fragment of the fragment shader. I'm using fragment a lot here. And what that means is that there are a couple of limitations, and that's one of the reasons we don't have preprocessor support. So here's what that shader code looks like. And I know this seems really weird, so I'll go through it a little bit if you haven't played with shading languages before. But basically, we start off with uniforms. And uniforms are a way of passing variables from Android to your shader. And this means you don't have to have a separate piece of shader code for every possible permutation. You can actually send variables to it. This is our main function, which is something that's specific to AGSL, and it contains the fragment coordinate. So that's the actual pixel coordinate within the view that you're actually trying to shade. And at the end, we return, we're taking this, I think, did I mention anything else about this? No. Oh, okay. Good. So I wanted to mention one other thing, is that shader there that you're seeing, that shader actually is a bitmap shader. And what that means is that's how we actually can sample an image. That's the other important thing I wanted to mention here. We actually send back a color. We're going to take that. Basically, as you can see, that hue rotation, we're literally doing a multiply. That multiply is actually a matrix multiplication, and we're multiplying it against a vector, and that turns into a color. So, what this particular matrix does is literally rotate the color based upon that radian value that we're passing in. So pretty fun. What does this look like inside of our Android code now? We compile the shader. We then have to apply these uniforms. And then we set our input shader. As I said, we use a bitmap shader. This is the way we put bitmaps into our shader. It is not... we can actually sample other shaders. So it's very similar to the way Compose shader at the very beginning of my talk allows you to combine shaders. This is also allowing you to combine shaders too. You can do things that are very, very, very slow this way by sampling something complicated. Bitmaps are pretty cheap, so that's why we're using them. And then finally, we create a shader effect with RenderEffect of that hue shader. So that's all the code it takes to actually execute this. What does this look like? If you want, you can try this out on your phone. One of the really cool things is that we've actually ported Skia to the web using WebAssembly, and so you can actually run Skia like on your phone, and it actually works and talks to WebGL, and so you can play with this. And if you tap on this on the mandrel on the screen, you can get it to rotate to different colors. It's based upon the x-coordinate of the mouse. And for those of you who aren't seeing, I should just show this because we have a little bit of time left. Let me see. All right, how am I going to mess myself up here? All right, so here we are. We have our mandrel. I have a mouse cursor somewhere. You can see it's running really, really fast. One of the things you can see is I'm actually calculating. I'm actually calculating the every single time I'm actually calculating this matrix, and that looks like it's going to be really, really slow. Look at all the sines and cosines and everything. But GPUs have a lot of hardware, and they run really fast. You can run your mouse across here. And you can see that we're actually, running this shader. And I ran it 4 times because I'm being fun. Let's see if I can get my slides back. Come on, slides. Oh, I thought it was going to be easier than that. Okay, we'll do this. We'll do this the old-fashioned hard way. There we go. Okay. So that's, and you can also really apply an effect to your existing render node content. So again, if you want to not apply an effect to a bitmap like I was showing you there, but you want to actually apply it to the contents of your view, you can actually get that by create RuntimeShader effect instead of create shader effect, and that allows you to pass in a second parameter, which is going to be a uniform for the shader that is being used to generate your view, essentially. So you can now sample the contents of your view, and you can shade that directly. And I don't have an example of that because I ran out of time. But there is one on the website that I did. So you don't also have to use RenderEffect to use shaders. RenderEffect is actually kind of slow because it actually creates a render node that actually creates a layer that actually does a whole bunch of things you might not want to do in your code. So we can actually just use it in Paint. So this is like the simplest possible shader code, basically. It just returns a color. No matter what its input is, it's going to return a color. And you can apply that really, really easily both to a custom view or to a Compose campus. And in Compose campus, you have to create a shader brush. I thought I explained this. And in a custom view, you actually make it. You add the shader to you set paint.shader. And so in both of these cases, you now are going to draw whatever is going to be drawn using that brush, which is pretty cool. You can do a lot of stuff with that. You can also do animations with uniforms. So if you want to see how this works, you can go to that and see a really simple animation. I'll do it for everyone, actually. We've we've got another 10 minutes or so, right? Let's see if that works. I'm waiting for my Chromebook to crash here. So that's what that does. You can see it's not very much code to actually do this animation. I'm just creating a triangle wave, and I'm using that to move this gradient, which I've generated inside of the shader. And again, it's all, maybe I can do this. Well, that's my LinkedIn profile. That's nice. No, that's not going to work. That's right, because I'm in Chrome. I've got to actually go to Chrome. Sorry. So that's what that looks like. And then finally back. All right. And then, and I'm leaving, this is the same thing. I'm just going to show how this works a little bit. So this is cool, is that basically you can take that uniform and you can use a value animator. And you can use that to send stuff into your shader. You can use that to, go and do whatever you want inside of there. In this case, I'm sending two. I'm setting a duration at a time. But as you can see, the time is being set by the value animator, and the duration is just a constant to make things easy for me. And again, that's what that looks like. So you can do a lot more to this. You can, of course, shade text. You can do this in the view system just by doing a paint. In Compose, you'll have to be using Compose 1.2. And you actually, inside of paragraph, you can actually draw a paragraph to a canvas, and you can use a brush to do that. So you can use a shader brush in just the exact way to do this, to shade text. And you can see I'm also doing animation here, which is pretty fun. You can also provide, put canvas animations on it. So this is an example of okay, we've got an animated shader inside of animated text that's spinning around. No one's going to actually want to do this in our app, but it was really fun, and that's kind of what these things are all about, is doing fun demos, and shaders make for really fun demos. And now I've shown this off a couple of times already, but you can debug your shader on Skia's site, because AGSL and SKSL, which is what Skia uses, are basically the same. There's a few missing constants, but like 99.9% of the time, if it works here, it's going to work fine on the phone. In fact, I have never yet had it fail, so that's great. Don't take that as necessarily perfect, but we'll see. And then let me get back into actually showing my slideshow here, Wow. Okay. And then, and I've done a couple things. I mentioned that blurring thing I was showing you earlier. This is, by the way, exactly the wrong way to do a Gaussian blur. This is a single pass Gaussian blur, which basically means that you have to sample each pixel in two directions twice. Normally what you do is you do it in one axis and then save that value off, and you do it in the other axis. It's much faster. Since I only have one shader that I can run, I had to do it this way. It just shows how fast GPUs are, the fact that this works at all. To be honest, and you can play with that as well. That one's not as interesting to look at. You just see you can actually play with the parameters, and you can change how blurry the mandrel is going to be by changing the radius. This one's also kind of fun. Just to show you how complicated these things can get. And again, you can port a lot of stuff from ShaderTor. You can't port everything. One is some of them are just ludicrously complicated, and a lot of them require OpenGL shading languages beyond what we do support in SKSL, but just to show you kind of what this looks like. Here you see you've got this really cool star field, and you can see on my Chromebook I'm getting about 37 frames a second with that. And this is just math. Like there's, you'd think there might be bitmaps or images or other things that are generating this, but like this is like magic math. It's a use of a lot of trigonometry, and I tried to analyze this, and I understand like 1/10 of what this is doing. So just to let you know, there are people who spend their whole lives coming up with amazing shaders, and it's just incredible what you can do with this kind of stuff. So if you ever wanted to have a star field on your text in your Android app, you can actually do that by taking the shader and porting it to Android. And again, this is the one that I've ported. If you go to that QR code, once again, you can actually see the code that I ported directly. And so finally, things to remember. So one, again, use RenderScript if you're targeting less than Android 10. You can use Vulkan to do compute if you're targeting beyond Android 10. You can probably get away with using AGSL for a lot of effects, however, that you would normally use RenderScript for. So if you're just taking a bitmap and shading it and then going to use that somewhere else in your UI, you can do that. If you want to use blur, you've got RenderEffect. And that's a really nice implementation of blur. It uses Skia's internal blur image filter, which is pretty fast. Intrinsics, we've got the RenderScript Intrinsics replacement toolkit. So if you want a nice, fast CPU-based version of those, that's great. It is like, I mean, sometimes because there's so much setup time involved in creating a RenderScript kernel, these things sometimes run like 5 times faster than they ran in RenderScript, just because, again, setup time is everything. So like, even if you're using AGSL and you're doing all of this because you've got to compile a shader and do a whole bunch of stuff and start the GPU up, it might actually be faster just to use this code. So I would definitely profile and see what works for you if you're looking for pure performance. If you want, the ability to not have any NDK in your project, then there are a whole bunch of solutions there. And of course, for YUV to RGB, which is the most used, let me step back a minute, the most used intrinsic is blur. The second most used intrinsic that we've seen is YUV to RGB. Camera X now does that for you. So as long as you can use Camera X, which the most used reason, the main reason you would use YUV to RGB conversion is because you were trying to get a preview from the camera, because the preview only comes in YUV. We now do that in Camera X in a reasonably speedy way, so you don't need to use this for that either. And then for other effects, you can use AGSL. There's a whole playground to play with. There's docs. I wrote the docs for this, so please send any errors. It's all my fault. And that's it for my talk, and those are the docs, so that's nothing very exciting. So now I can take questions.